This is the last video in Module 9 of my series on computer systems. In this one, we're going to take just a quick look at embedded operating systems. We've talked about quite a few different approaches to operating systems before, so let's take a quick look and find out what an embedded operating system is and get an idea of what kinds of things they're used for. So, an embedded system refers to the use of electronics and software within a product that's designed to perform some dedicated function. In a lot of cases, embedded systems are going to be part of a larger system or project. So, anti-lock braking systems or airbag control systems in a car would be some great examples of embedded systems and how they're used. Now, here's one possible organization of an embedded system. Of course, we have to have a processor, right? We've got to have some kind of piece of hardware that can actually do our computations. But we're also going to have, starting from the lower left of this diagram, we'll have sensors, right, that are going to go to some kind of electromechanical backup and safety. If we're talking about keeping it with the whole car thing, the anti-lock braking system or the airbag system, right? So we've got sensors, we've got analog to digital conversion that talks to the processor, we've got a human interface hooked up into the processor, right? So the processor knows what's happening in the car, whether we're hitting the brakes or turning the wheel, etc. We can have some kind of field programmable gate array that's doing some stuff, that's running some software for us. We've got a little bit of memory, because of course we have to have some memory for a computer system and if we're going to do anything with it. We've got auxiliary systems like power and cooling, some kind of diagnostic port usually, right? We have to be able to get in there and access the processor, find out if everything's going okay. A digital to analog conversion that would hook out to the actuators for, once again, whether we're going to use those actuators to engage an anti-lock brake system or to deploy a airbag or something along those lines. Right here, this is just one way that we can arrange an embedded system to accomplish that goal and get all the information that it needs to that processor so that it can actually engage things when we need to engage them. And this, of course, if we think back to our module on scheduling, this is the kind of thing when we're talking about safety systems in a car, this is the kind of thing where we're going to be talking about some real-time necessity, right? We have to do things with an eye toward making things happen as quickly as possible, right? Because we definitely don't want the airbag to deploy late if we're in a crash. So some characteristics of embedded operating systems. We have real-time operation, like I was just talking about. We have reactive operation, right? We need to be able to react to external influences to the physical world. We want some kind of configurability. We need I/O device flexibility, streamlined protection mechanisms, and we have to use interrupts directly. We have to process interrupts very, very quickly. We don't have time for a level of abstraction or a layer of abstraction between the processor and the interrupts that are coming in. So when we develop an embedded operating system, we have two general approaches. We can take an existing operating system and adapt it for the embedded application, or I can design and implement an OS intended solely for embedded use. So, I could take a Linux kernel and strip it way down, right, and adapt it for some embedded application, or I can just start from scratch and develop the entire operating system right from the ground up. So all we need to do to adapt an existing operating system to use for an embedded system, we can just add real-time capability, we can add some streamlining of the operation, we can add some necessary functionality, and that's nice because we have a familiar interface. We've got a lot of the bare bones, a lot of the basics of it already there for us, and we just strip it down and add what we need to do. But there are some disadvantages in that it's not going to be optimized for real-time and embedded applications. Right? As much, if we actually did everything we would need to do to modify an existing operating system to really be optimized for real-time embedded applications, we're probably better off just purpose building an embedded OS, right from scratch. Now, when we do that, when we build an embedded OS for the particular purpose that it's going to be run for, we've got some typical characteristics. It's going to be fast and lightweight processor thread switching. The scheduling policy is going to need to be real time, and the dispatcher module will be part of the scheduler. It's going to be very small in size. It's going to respond to external interrupts very quickly. We're going to minimize intervals during which the interrupts are disabled, right? We always want to be sure that we're getting those interrupts as soon as we can. We're going to provide fixed or variable size partitions for memory management because we know exactly what's going to be happening. And we can provide special sequential files that can accumulate data at a fast rate. So when we build an operating system for the purpose of being embedded, for the purpose of running embedded applications, we really can make sure that we make something that is absolutely optimized as much as we can possibly make it for what we need to do and for the requirements of embedded applications. A couple examples are ECOS or TinyOS. And those are a couple things that you can kind of Google and see what they do for you. But they're very, very tiny. They're very, very good about meeting all of these characteristics. Now, we have timing constraints, right? We're talking real time here. We have to do some stuff in the kernel to make sure that we're dealing with timing constraints properly for a real-time embedded system. We need to provide bounded execution time for primitives, maintain a real-time clock, right? We have to have special alarms and timeouts. We have to support real-time queuing disciplines, right? We've got to be able to do real-time scheduling with this thing. And we have to provide primitives to delay processing by a fixed amount of time or to suspend or resume execution when we want to, right? We don't want to leave that to chance because, again, in a lot of cases, we're talking about systems where life and limb could be at stake if these things fail, if these things don't meet their deadlines. And that kind of goes back to what we were talking about when we were talking about real-time scheduling in previous modules. Now, embedded Linux is a version of Linux running in an embedded system, right? They are going to require support for a specific set of devices, peripherals, protocols, depending on what hardware is present. And in a lot of cases, when we're talking about embedded systems, we're kind of designing it around the overall external system as well, right? We know what's going to go into the car that we're putting our embedded system in. If we're designing an embedded system to help us control safety features in a car that we're manufacturing, we know exactly what's going to go in there. So we're going to minimize, and make absolutely sure that we only use as many cycles as we absolutely have to for kind of running the operating system. We want to make sure that we're not taking time away from responding to interrupts and doing what we need to do with the system. Now, a big difference between like a desktop or server version of Linux that you might run on, well, a web server or on your notebook, and embedded Linux distributions is that the desktop and server software is going to be compiled on the platform where it's going to execute. An embedded Linux distribution are usually going to be compiled on one platform but executed on another. So we use a software called a cross compiler, so I can compile it on my desktop and then run it on the embedded system where it's going to live. Some advantages of this are vendor independence, right? The platform provider is not dependent on a particular vendor to provide the features and meet deadlines for deployment. We can have varied hardware support, right? Linux supports a wide range of architectures and peripherals. It's low cost, right? Use of Linux minimizes cost for development and training. It's a very commonly used system. It's also open source for the most part, unless you go to one of the actual for-cost Unix flavors. So we have all the advantages of the open source software as well. We have this being maintained and improved by a community rather than, again, having to wait for a private third party to do things and just sort of hope that they're doing what they need to do properly. We'll also, because it's open source, of course, have access to every line of code that goes into this thing so that we can do our own controls and do our own code review and make sure that, again, somebody else hasn't messed up what we need for a very important embedded system. Now, I'm going to finish this video with a little bit of a look at Android just because there's some debate, honestly, about Android, and I'm not going to come down on either side of it, but I want you to be aware that when we talk about Android, it can be defined as an embedded OS based on a Linux kernel, or we can consider it a platform OS that can support a variety of applications that vary from one platform to the next, right? It's a vertically integrated system, But the deal is we've got the Linux kernel, we got the Android user space components that run on top of it. Some folks consider Android to be an embedded operating system. Some embedded, or actually a lot of embedded Linux developers don't consider Android to be an instance of embedded Linux because a classic embedded device has a fixed function, right? It's frozen at the factory. We have the operating system, whether we adapt it or kind of custom make it. We get it set up, we optimize it as much as we can, we add those components we need to add. On top of it, we get our application in place and it gets frozen, right? It gets fixed. It's frozen at the factory and it just goes out and does its thing. Now, Android, of course, we can install new applications, we can do updates, we can do all sorts of different things right from the device that we're holding. So it's got a lot of flexibility, and the functioning of it is not fixed, right? We can change that pretty much as we want. Nothing is frozen at the factory almost. That being the case, a lot of embedded developers don't consider Android to be an instance of an embedded system. So that I just wanted to let you know, because that's one of those things that you'll find people screaming and yelling about on forums. So it's good to be aware that there's some difference of opinion on that.